Welcome to August 5th's LeetCode Challenge Stone Game. Alex and Lee play a game of pile stones. There are even numbers of piles arranged in a row. Each pile has a positive integer numbers of stones piled at I. The objective of the game is to end the game with the most stones. The total number of stones is odd, and there are no ties. Let's see. Alex and Lee take turns, Alex starting first. Each turn, a player takes an entire pile of stones either from the beginning or the end of the row. This continues, and that there are no more piles left, which person returns the most amount of wins. Assuming Alex and Lee play optimally, return true if and only Alex wins the game. Alright, so we have an example here. It returns true because Alex won the game. So basically, Alex starts first. He takes 5 in the beginning or 5 at the end. Doesn't matter. Well, it does, but it takes it from the beginning, and then Lee takes it from the 5 from the other end, and I'll say Lee takes it from 3. Then the board is now 4-5. Alex takes the ending 5 to win, and now the board ends with 4. So basically, this demonstrates that taking the first 5 will be winning, so Alex will win will be true. So basically it's saying return true if and only if Alex wins the game. And so if we just were to use so let's see, if there's 2 piles, let's just assume let's just think of a scenario where there's only 2 piles instead of 4 piles here, 2 piles. Alex will always win when there's 2 piles, as you can see, because if each player plays optimally and there's only 2 choices, Alex will choose the biggest pile, right? The pile with the largest amount of number, and he always starts first. So that means that Alex always wins when there's 2 piles, and then you can do the same thing with you can extend by induction. You could do the same thing with 4 piles. So if Alex takes the first pile initially, and then she takes the 3rd pile. If she takes the 4th pile initially, then she goes over with the 2nd pile afterwards. So it'd be 1 plus the 3rd, 2nd plus the 4th. So whatever wins is larger, right? So she will always win. If she goes first, which is true, if and only if return true if she wins, and if there is a even number of piles arranged in a row, right? So if there's even amount of piles, Alex will always win. And also this, so we extend this to n ideas as well. The n piles. Say say the 1st, 3rd, 5th, 7th piles, right? And Lee were to pick the 2nd, 4th, 6th, and 8th piles. Alex will either take all the piles that are bigger, or she will take the ones that are smaller. And obviously, she wants to win optimally. So therefore, the sum of the number of piles that are larger that she will take. So hence, Alex will actually always win the game if there's an even number of piles. So let's return true if Alex only wins, right? And that's it. That's a mathematical way of interpreting it because the solution accepted. So basically, the conditions kind of have to fit such that Alex starts first, and the even number of piles, and that there are total number of stones are odd, so there are no ties. Then we only return true if Alex wins. So if we only return true if this thing succeeds, essentially, and that gets accepted. That's not really satisfying, to be honest. Well, it actually is very cool to understand that. It's time and space complexity is big O of constant time, because we just run the function as it is. Let's just make it a little bit more challenging on ourselves and go with a classic dynamic programming approach here. I'm going to use a bottoms-up solution. So this is solution number 2, which is a bit more challenging, but it's understandable, and it's using a bottoms-up dynamic programming solution. Let's go with that. So the first thing we want to do is define the length of the pile. So I'm going to call that n. N equals the length of the pile. And then we want to develop a dynamic programming array with initialized to n. And then I'm going to run a for loop here to iterate through each of the number of piles in reverse order one at a time. So for I in range, so the span is going to be n minus 1, reversing in order and going backwards and decrementing it. And then for each of the piles, I'm going to count the number of stones. Is it stones? Yeah, stones in each pile. For j in range of I plus 1 to n, right? So we're going to update our dynamic programming array, so dp at index j, and that's going to be assigned to the max. We're going to find the maximum, basically, as we traverse along piles at index I, minus the dynamic programming array at index j. So we want to find either this is the max pile, so at pile, basically at piles index I, if that minus the pile at minus number of stones we have, right? If that's the max, or if the piles at index j minus the dynamic programming array at index j minus 1, right? Or the one before it is larger. So basically, we want to update that to find the maximum amount of maximum of stones we have, and then we want to return the maximum number of whoever the winner is. So basically, we want to find if it's true or not that the person wins, right? Because this function only takes the number of piles, and Alex always goes first. So we want to know if the number of piles is large or not, which is always going to be true if the dynamic programming array at the index n minus 1 is greater than 0. That just means that the second last person is greater than 0 in the dynamic programming array, because remember, if Alex to go first, that means that Lee has to go last. And then we're gonna run this. Submit. Okay, this is accepted as well. This is using a bottoms-up dynamic programming approach. Time complexity is big O of n squared because we have a nested for loop. Space complexity is big O of n because we have a dynamic programming array here, which stores at most n amount of piles. The length of piles. Okay, that's it. Have a great day, guys.